What's up, everybody? First of all, I just want to make a small apology about not streaming anymore last week, like I had mentioned at the end of my live stream. The integral engine stuff in qcrab, coming from libint, was pretty crazy. Um, and actually, I had to give up on it eventually and just compute the integrals. Uh, I finished the overlap integrals, and I'm planning to make like a summary video. I'm not sure that live streaming, me kind of beating my head on the wall uh, on some aspects of that problem is a good idea. So I'm just going to try to do like a summary video and maybe some tutorial videos at some point about how you could go about writing your own quantum chemistry code, because it's a little bit harder and the resources are a little bit sparser than I had anticipated. So I think that will be coming up shortly. Probably not going to have qcrab live streams, um, unless it's small stuff. I thought about live streaming today, but settled on a video instead. So anyway, with all that aside, the main point today is to load some basis sets from files that we can get from the basis set exchange. Um, Basically, I got the basic overlap integrals working last week, and I can now pass my existing tests using my overlap integrals, which was really exciting. But I've only tested so far with STO3G, and I'd like to test on the two other basis sets, DZ and DZP, that are in the that were in the Crawford projects. And there's also one slightly scary thing. I had to reduce raise my epsilon value on the methane test from like 1 times 10 to the minus 12 to 1 times 10 to the minus 7. So there's a possibility that there's something wrong in my, let's see. Anyway, there's some chance there's something wrong in the code I wrote. But I think that's still pretty good agreement, and I'm hoping it's just a difference between like the geometry and the integrals we got from the Crawford projects. I think I mentioned in the last live stream that there is some chance that the geometry in the Crawford project is not the geometry at which the integrals in the Crawford project was computed. And now that I'm computing my own integrals and actually using the geometry to get some of the integrals, it might introduce some disparities there. So I'm hoping that's what the issue is, but I'm hoping now that trying these other basis sets might reveal something like that. Okay, so with that said, let's jump into it. I don't care. I'm not using the hotkey. At the last live stream, I forgot to change the scene, so I'm just gonna make sure it changes. Now, I've already been over here looking at the basis set exchange, trying to pick out a nice format to use. So they have many formats available. I looked at the Gaussian format. I looked at the MolPro format. Those are the two main quantum chemistry programs I'm familiar with. But I think we're just going to go for this JSON format. And you can see I've already been playing a little bit with JQ over here. So we're just going to drill straight in to the elements. In this case, I've selected element 8, but we're going to end up having to loop over the elements. Well, we won't have to loop over the elements. The nice thing about using JSON is that we can just use serde, or serde, however people pronounce it, to serialize and deserialize our basis sets from the JSON. So we're going to just deserialize this into an array of elements, or vector of elements, which will in turn include these vectors of electron shells. And then from there, I think it's going to be pretty easy to transform these into our basis sets, which look like this. So I did make a new type for a basis, which is just a vector of shells. And if we look at shell, oh, let me go back. I'll do that again. So I made a new type called basis that is just a vector of shells. And if we look at shells, we have a vector of exponents, and a vector of contractions. Although, following libint, we can only handle single contractions right now, so this doesn't really need to be a vector, but whatever. I guess it's okay for now. And then we have the origin of the shell. Then we can go look at contraction, and contraction has angular momentum, whether or not it's spherical. Actually, where do we use this? And then it has contraction coefficients. Let me actually take a look where we use this. If self.pure. It looks like this is the only place we use it. 2 times. And where do we use this? I'm wondering this because the third basis set used in the Crawford projects is the DZP basis set, and it actually has a mix of one of the d orbital says that the type is GTO spherical. So I'm wondering if this spherical stuff is actually going to pop up now. Let's see, so there's the definition, and we use it here. So this is shell size, is just mapping over the contractions and getting their size. So do we actually use this? So I do use this to get the number of atomic orbitals. I use it here to get the number of basis functions. I guess we do use it. Why is it not? Okay. I guess we do use it. Yeah, so I don't want to spoil too much of this. How are we going to fill this in? Oh my goodness. I think we really want this to be Cartesian, right? Yeah, we're probably going to run into trouble with the d orbitals. And again, I'm going to plan to make a video on the actual overlap integrals later. So it's mostly what we were able to get from libint, with some additions, especially around here, to handle the higher angular momentum functions. And I'll probably do a video going through what I ran into in libint and why it was so hard to continue following the code. Because they did when they were both s orbitals, they set this variable that was aptly named called compute directly. And then they would do code like this to compute the value directly. But when I need to factor this into a function because it's the same in both places, there's more to do here. But I was just really happy to get it to work. But if compute directly was not true, it was just this crazy mess of macros. And basically, I'm convinced that the code doesn't exist in the repository. Like, I don't think I can actually read the code. I think it's produced by the expansion of all of these macros when the code's compiled. And I might be wrong about that. Probably people more familiar with C++ could tell me whether or not that's true. But anyway, it was impossible for me to find the actual code that computed these integrals. So I've added some references to this repository. So if you guys are curious, you can take a look. I think I updated the README as well. So these are and I think all of these, I found PDFs of all of these, except the libint source code, just open online. So I've put them all in this repository. So if you're curious, you can go have a look there. But those are what I had to turn to get these integrals going. Now, let's turn our attention back to basis. And basically what we're going to do, I think, is there a new? I guess there's not a new function, but. So what I'm going to do, basically, I'm going to come up here, and we're going to have a pub. This is probably just pub. Pub fn. I'm going to call it load, and I guess it's going to take. I guess we can just take a path, which is going to be as ref path. I guess it has to be impl that. I always forget. and it's going to return a self. Okay, yep, so it'll be, we can take any path, because what we're going to do with the path is read it. Now, let's take a look at our TOML file. Since we're doing JSON, we're going to need both serde. I'm just going to call it serde. I know John Who calls it serde. I guess it's probably supposed to be serde because it's serialized, deserialize, but it looks like serde to me, so I'm just going to go with serde. I guess I'll go. The only thing I want to check here are the versions and the features. I think we actually want to go back here using, here we go, because we're going to derive, yeah, of course we want to derive it. Great. Okay, and then I guess we want this as well. No standard. I'm pretty sure this one you can just cargo add serde 1087. Is that right? 1087. Great. So we now have both of those. And the only thing we really have to worry about here is we're going to have to build a struct that looks kind of like this. There's probably a way around this, but that's the easiest thing I know how to do. Probably we could implement deserialize ourselves or something like that, but I think I'm just going to do it like this. So this will probably be a new module. I'm just going to call it JSON basis, I think. Or maybe we can just call it JSON, because it'll be in our basis module. Mod JSON. Struct. What do we want to call it? Maybe this is what we call JSON basis. So it's going to have a vector of elements. Let's see what we got here. Now these might actually be hash maps. So this is the atomic number, right? And it's a map of this to this stuff. But really, we really just care about, yeah, 2 electron shells. All right, let's see what we can do here. Vec of hash map. Does it need to be? No, it just is a hash map. Okay, hold on. It is a hash map of usize to shells. Well, I don't really want to call them shells again. Let's see. What I often do is I call them just raw something, because this is what's going to be loaded in, and then we will process it. So it's in this raw state, right? Then we can introduce this raw shell, and we'll just put in all of this stuff. Well, at least the ones we care about. So I think we don't care about the function type. And I think we don't care about the region. We do care about angular momentum, which should just be a usize. And we do, of course, care about exponents. which is a vec f64, and we care about coefficients, which is also a vec f64. Oh, let's see. Electron shells. Oh, okay, it is a vector vec raw shell. Okay, and now we're going to try to derive deserialize on this. Import it. Oh, I probably, I think I changed my rust up default nightly. I might have to clean this, we'll see. Obviously it's not going to compile. Okay, well that's fine. That's the best possible reason for it not to compile. Good, good. Okay, so yeah, these these warnings are just wrong. Perfect. That's what I like to see from my from Emacs, of course. All right, so let's see if we can call this from JSON. Well, okay, hold on. Let's just read to string path. We're just gonna unwrap in here for now. Probably should return a result, right? But that's okay. Let's call it this. Unwrap. Great. And then we're gonna use serde JSON from string data. Let's see what we got here. JSON basis. Let raw base. Well, let's call it raw equal this. This is a result, I think. Yep. Might just be pub crate. I think we can even do pub super, but oh, I haven't used load yet. So I need to actually write a test, of course. Oh, test. Load. And oh, I have to give it a molecule. Yeah, and I guess basis. Okay, there we go. Okay, now shell needs that. Well, you can see how far I got with my TDD since These don't have any of these derivations on them. Okay. No. Map expected a sequence. Okay. Okay. Electron shells has to be a vector, I guess. I thought we did do that. Electron shells. Elements. Ugh. Oh, Rust. Backtrace. I don't think that's going to help us. Line 9, column 13. Yeah. I think it is. I think it does have to be vec hash map. Is that right? Ooh. Map expected a sequence. Now it says line 8. Okay. Okay, so apparently this hash map was right. Okay. So I guess this is a map to this, where we only care about our electron shells. Okay. Let's hold on a second. Shells. Struct shells has electron shells, which is a vector, a raw shell. Okay, let's take this again. Try that. No, line 14. Angular momentum. Oh, duh. Did it work? String. Wow, that's interesting. Why can't it convert that? 18. Alright, well, I guess we just have to make these strings, and we'll do the conversion ourselves. That's the exponents. String. I'm assuming the same problem will happen for coefficients. Expected a string. Line 23. Oh, vec. There we go. Okay. So we've handled the raw part in load. Okay, perfect. So we got this raw part. Okay. So I think this is unused because I think we're in a private module. Pub create mod bases. And then if I do mod lib int, that's also not pub. Yeah. So this is going to give us a dead code warning. Now, we want to see if we can make that look a little better. There we go. Oh, and this is gonna have to. This has to take a molecule as well, actually. Oh. You have to load a basis set for a given molecule. Okay. I'm not sure actually this is the approach you want to take. We might want to stick at eventually to having something like this, where you request a basis set. Yeah, this is like a good, because we can download these JSON basis sets that just have like every element in them. Yeah. And then we can turn them into things like this. Okay, that's something to think about. But for now, let's just get this working. Well, we do have to. We'll give it a molecule for now. So, okay, load the basis set from path and something like that. I don't know. We'll just copy this, I think. Actually, we can probably use some of the... Well, maybe not. Okay. We need to take mole. Whoa. Oh, there we go. Let me shells. So, this is what we got. No, this is what we want. Whoops. Let's just do this. Isn't it something like this? Oh, it doesn't. No. We don't do serialize. I guess we can derive serialize, right? No, that's dumb. Just do it like this. It needs to derive debug. One thing I wish that Rust Analyzer would do is sort these alphabetically. Now, I guess probably molecule up here. Maybe there are cases where you don't actually want them to be sorted. I don't know. All right, atomic number. So what are we going to do now? This isn't I size, right? U size. So we need to look in raw. Create raw dot elements of, and we're just gonna use the braces to index it, because if, well, and then we can add this to the comment, right? Panics if path cannot be read, if its data cannot be deserialized, and if it does not contain one of the elements in mul. Okay, so this thing really wants to panic. Which again, we should probably return a result. But this is kind of an... I don't know. This is kind of an internal function, so maybe it's not even pub. Maybe it's just pub create. We'll see. I have no idea what the public interface for this this program will look like. Okay, so we're going to try to get this, and for now, why don't we just debug it? Well, I want to print it nicely, which I'm doing this. Okay. Raw. This is also private. Create. Actually, yeah, again, it should probably be pub super. So I think it's going to panic. Yeah, no entry found for key. Because I only downloaded the one for oxygen, but we need also hydrogen. So 3G. It's not a fuzzy search. HCO, I think, is all we need for this. JSON, get basis set. Yeah, copy to clipboard, perfect. Okay. Yeah. All right, now that. Okay, excellent. Let me shells. Okay, we're gonna fix that. We're gonna fix that. Elements is never read. We're gonna fix that. Okay, so that's the whole basis. Great. Shells, raw elements, atomic number. Yeah, so for shell in whoops, dot elect shells. This is private too. Now we're going to do shell new. Basically, we want something like this. Basically this exactly. Except without the match. What's the problem here? Do I have to borrow it? Okay, so for shell in raw elements, atomic number, electron shells. Okay, this is the contraction. This is L. So this is going to be shell dot angular momentum, which is private. Well, this. Oh. Okay, hold on. Angular momentum, exponents, coefficients. Okay. Okay, so for each shell, yeah, we can then loop over the angular momentum. Okay. For L in shell dot angular momentum. L. We'll stick with false. I think this is the origin, right? Yeah. No, this is coef. So let's go IL 0. No. Is that right? Yes. No, that's right. il.iter enumerate. Because, at least I'm assuming, I hope this is the case, that the length of angular momentum is the same as the length of coefficients. So we're going to try, we're going to use this I to index our coefficients at the same level as our angular momentum. Okay, so now, take this off. Okay, so shell new takes alpha. Those are the exponents. This is slightly annoying, but I guess we're going to do it. This is for hydrogen. Let's go look at hydrogen. Hydrogen. 342. Yep, that looks right. 6239, 168. And these are our coefficients. 3. Yeah. All right. We got the right numbers at least. Let's come back down here. Shells.push shell new. The first argument is alpha, so those are the exponents. Shell. Poor shell. Yeah, it looks like within a shell, we only have one set of exponents. So let's do this. Let alpha equal shell dot exponents dot map. S dot parse unwrap collect. Yeah, of course we have to iter into iter. Well, we can't do into iter, right? Because we're borrowing it. And we want this to be a vec. Actually, if I say vec f64, maybe I can take this, the turbo fish off. We're going to have to clone it, I think. Great. And now we just need to actually handle the coefficients. Let coef equal. See, it's a little bit sad. We only have to clone it. We don't have to clone it every time. We only have to clone it until the last iteration. Whatever. Coef is actually going to be basically the same. It's just shell dot coefficients of I dot iter dot map dot collect. And then this will be coef. And that might work. That might be it. Probably not, but maybe. Alright, let's see what's wrong. So this is now what we got. Oh, of course they're not going to be quite right. Whoa. 2, 3, 4, 5. Let's make sure the length is the same. Okay, the length looks the same. Where am I printing that? Let's stop printing that. Okay. So as we noticed when we were, well, as I noticed when I was looking at the JSON, there are more decimal places in the file than in what we had in our code. So let's see. This is one. Let's see how it looks. 70932 886 643. Contraction 0. Pure is false. Coefficients. Origin. This is looking good. 0, 0, false, false. Coefficients look good. 0, 0, same origin. Okay, this looks good to me. 396, contraction. L1, pure false. Okay. Yeah, so I'm thinking that the issue is only that these numbers are not exactly the same. This is a good use of the approx crate, but if we use approx, then we have to implement abs.deq ourselves. So probably what I'm going to do, after I spot check this, not spot check, I mean I'm checking it all the way through. After I check this myself, I'm just going to copy what we got to what we want, basically. 6783413. Yep. This looks great. Of course, the next test has to be a different basis set that we don't have. 83471638. That looks good. So let's just go up here. Whoa. Where am I? Yank in square bracket. And we'll say let one. Basis. This is a little crazy. Yeah, these are supposed to be vex, of course. Why did it do this? Origin is supposed to be origin. Oh, that's funny. I think this is a vector. Probably gonna have to import that. Okay. What? Oh, then we got these curly braces. This is supposed to be a vec. Vec. What's the problem here? Vec. Vector. Vec. Vec. It's not actually complaining about this, but I think it needs to be a vec as well. Vector. This is, yeah, this is my type alias for a 3 vector. Vec, vector, vec, vector. I wonder if this is another private thing. Mismatch type, yeah, coa, vec. Alright, what now? Mismatch types. Oh, I missed this one. This oh. Ooh. Here. What's wrong now? Oh, great. We're just getting product macro warnings. Cannot create expander. Let's try target clean real quick. I've done some weird like switching back and forth between my default toolchain, actually to build Paru. Yeah, that's always annoying. Yeah, I don't know. Okay, so it looks like this passes. And I don't use... Yeah, very nice. Very nice warning. Oh, it's because of the test. Duh. I need to put this somewhere else. Anyway. Let's go back to HF tests. Alright. If test.dir contains sto3g, we're going to load our bases from basis set / sto3g.json. So now let's see if we can. Oh no. Okay, that's a bit sad. 3, 4, 5, 6, 7. Yeah. Okay. Well, maybe that's approximately what went wrong before. We might have to go down to 7s everywhere. Let's see if it works for carbon. Pass. Okay. Let's go get the DZ. We're gonna try this. Hold on. Undo. If test.dir contains sto3g, this is gonna look a little bit ugly for a second. We'll fix it later. Test.dir.contains. Actually, we can't do. How about ends with DZ? Okay. Now this should crash, of course. Okay, so let's go grab the DZ bases. Yep, Donning Hay. Get basis set. DZ.json. Let's try this. Let's see if it works. It looks like it's working, I think. Oh, we passed. Oh, we passed. That's fantastic. Okay, so that's great. Oh, that's wonderful. So what I'm going to go ahead and guess is these 1e minus 7s. Is that somebody? I kind of guess that somebody put the sto3g basis set in manually, which is why our manual sto3g basis set worked. But when they went to the larger basis sets, they loaded them like we did here, so it didn't work. So ours worked with the loaded basis set. Let me make sure that this is actually even running. Well, the other way you can do this is just panic. Yay. Okay, so it's definitely working. Great. So I think that's probably going to cut the video there. Hopefully this is interesting to you guys. I do also want to, well, maybe I'll show you guys my the test failing, because I need to do some work on d orbitals, I think. Test.dir.ends with dzp. Now again, this is not how this should work. This this if-else thing is kind of ridiculous. Especially because this code is the same. So basically, all I need to do is check the... We'll probably still have this else if on the dir. But I can just have it return this, so that I can move the mole shells, overlap ints, all into one thing. But anyway, let's go ahead and put dzp in. dzp. This one. Get basis set. So in Brave, it doesn't do this. It puts them all over here. But just to show you what I was talking about. Oh wait, it does just say GTO. Oh, because that's for hydrogen. 6. So we got GTO, 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 GTO spherical. So that's very scary. And the other thing that is scary is this 2. It doesn't look that scary, but that's a d orbital. And I was having a hard time figuring out how to treat p orbitals, but I think I have it all figured out now. We're going to try to handle d orbitals today. dzp. Great. Now this will definitely fail. It will probably even crash. Unmatched L value. Yeah. Perfect. Okay. I guess I can just comment this out for now. And we should pass again. But anyway, gonna cut the video there, guys. Thanks for watching. I hope this is still interesting to you all. We got to see a little bit how to use serde or serde today. Probably not in the best way, but at least we got it going. The plan for me today, I'm probably going to try to figure out these d orbitals and get this running. And once I do that, I'll be moving on to these other types of orbitals. Kinetic energy and nuclear attraction, and then eventually the electron-electron repulsion integrals, or ERIs. Yeah, so yeah, thanks again for following along, and I'll see you next time.